discuss now a question also of interest, which is the distribution of the length. All right, so for this, the idea is to see that there is a difference, that this is small, and this is in principle much bigger, 10 times bigger. And so now we're talking about part 2. So this was introduction. Now we are part 2, which is really analysis. So for this, we are just going to rescale things. We're going to call x equal L minus L0 divided by R by A. Lambda x is equal 1 divided by 1 plus beta x. B, so those are normalized variable. B is A multiplied by beta. And we're going to normalize also this exponential probability. So the probability of the scaled variable psi equals y is theta exponential minus theta y. And theta here is, this is just A multiplied by P. So you divide by A, so you have to see each, basically your process is you divide everything here by A, and you see how this propagates everywhere. So now the idea, I want to inject all of this into a time-dependent process. I call it delta t, the time in between two divisions. So let's rewrite the process. Instead of calling ln plus 1, I'll call it xt plus delta t. T is the discretization, I suppose, of the time, and we're going to write it x of t minus delta t, and x of t here plus psi. Now this is this probability 1, the rate, minus lambda x delta t, and this is with probability lambda x delta t. And in principle, delta t here is 1. Delta t is 1 if you differentiate, if you divide everything by A, you get ln minus 1. This is a new variable. And so we have changed it according to psi divided by A. Why we're doing that is to inject everything back into some kind of continuum process. So now, if you look, did I say what is lambda x? Yeah, lambda x is given by here. Okay. So now, what's the probability? Now we're going to write the equation for the transition probability. So let's see what happens between two divisions. So how do you go from time t to t plus delta t? Let's assume that you end up with a length x. So what happened? Either you started at a length x plus delta t, and with a probability lambda x delta t you increased. So we started with a probability of having x plus delta t and time t, and with this probability you made your transition. Or, and then we have to sum because it's going to be a distribution. You were somewhere with x minus z, so you are, and then you have to add something of size z to arrive to x. So multiply by wz multiplied by the transition probability, which is this one, which is lambda add transition probability, which is lambda x minus z multiplied by delta t. And then you have to integrate over all the z from 0 to x. Right? Because you can only add. Okay, so now if we have to do a Taylor expansion of everything in delta t. So this can be written as probability of x and t plus the derivative dp dx multiplied by delta t plus something that you can neglect in delta t. This I can always approximate as lambda x plus delta t. Delta t, suppose, is small, and you have delta t multiplied by delta t is going to be squared. So this can be approximated only as lambda x. I can write it lambda prime x delta t multiplied by delta t, so I get delta t squared here. So this will be negligible compared to this one. And this guy, can go in here, and I will divide everything by delta t. So what happens when you do all of this? So basically, the idea again, you have this systematic shift. It's like a drift. This is why you are going to get some kind of hyperbolic equation in one direction. So again, let me please double check that I'm not making any mistake in the calculation. So this is x t plus delta t minus p of x t, and now let's divide by delta t. So I have moved this guy in here, and I divide by delta t. So then if I divide everything by delta t, the delta t here goes away, and I'm left with delta x, delta p here, and this is multiplied by 1 minus. So this stays, so this is, what did I say? dp dx, x and t. All right, now next, the term, I have p, yeah, is there, so p multiplied, I think I have the term p multiplied by this, divided by delta t, that should stay. So we have minus lambda x, p x of t, plus, and then it's like a convolution, so I can invert if integration dz. If I'm integrating this dz, I can just write y equal x minus z, so I can either put this in here or leave it like this. What am I doing? Yeah, so you can always rewrite this. It's integration from 0 to x of lambda y p x, or p no. Yeah, py t multiplied by w x minus y. And what is, how we defined everything? Yes, the y here, I'm sorry, the y here corresponds to the probability to this here. So this is p, right? This is the probability of making the jump. So this should be py. Okay, so this, when delta t goes to 0, this is exactly the limit of this. When delta t goes to 0, this is exactly dp dt. So you get what is called partial integral differential equation. Yep. So dp dt equals, yeah, this is correct, lambda x. So this says that if we know how to solve this, basically we'll get the information about this transition probability. So the time-dependent we didn't look, because we were interested in the question number 1, which is a steady state distribution. And the steady state distribution is you take dp dt equals 0. You impose that your distribution is normalized to 1, because obviously this is up to a constant. When you have this is 0, so everything is linear, so up to a constant, you'll have your solution. And now, actually, I'll give you the change of variables. So this is a bit analytically not that interesting, but I'll give you the changes of variable. If you just do this, and we call P tilde the solution at steady state. This is a steady state solution. So let's call it F tilde. So F tilde of X. Basically, the new variable here, you take this as a new variable, right? And now we have to replace. So lambda xf, this is u, so it's going to give you minus u, plus integral from this is exactly uy. W, this is the exponential here, so there is some theta somewhere. Theta, and then you get exponential minus theta or plus theta y, and here you have the x, that is exponential minus theta x. You have to integrate from 0 to x, and then differentiating dp dx, which is df dx. So f tilde of x, this is u of x multiplied by lambda, but lambda is 1 plus this, so 1 divided by lambda is 1 plus beta x. 1 plus beta x, so it's very easy when you differentiate this. This is just the derivative of this plus beta u, correct? So you just plug this into here. What u prime 1 plus beta x. And here we end up plus beta minus 1 u plus, I don't know why I don't have the theta. All right, so I'm not going to be equal 0. So now this is becoming just calculation. I will skip some steps. But basically, what do you want to do now? You have u integral of u, and here you have something with derivative. So you just have to put this term in here and just differentiate one more, and you get a second order differential equation in u. You get u second, u prime, and u. And this you can solve, and this is associated to what is called the degenerated hypergeometric function. Okay, I think it's not that interesting that I do the calculation. I just wanted to explain the method that you arrive to here. And you can solve this equation, and you'll see you end up here with a distribution, a non-distribution. All right, let me skip the detail. I mean, I can just differentiate and let me skip this. It's not that interesting in terms of just calculations. So when you do all of this, and you use that, of course, your solution has to be bounded in L1. Fx is actually what is called, this is called a gamma distribution, which is basically, so f of x, where you have only an exponential here. Okay, let me write it down. Theta plus 1 over b divided by theta, correct. So this is theta x plus 1 over b to the power 1 over b exponential minus theta of x plus 1 over b divided by the gamma incomplete gamma function, which is 1 divided by beta plus 1 theta divided by b, where the incomplete gamma function, so the gamma function, the incomplete one, is defined by gamma s and x with the integral from x to infinity of ts minus 1 exponential minus t dt. And b, we have, this is here, a multiplied by beta. So this answers the first question. What is the steady state distribution? Right? You can have everything. It's given in terms of the parameter of the problem. We have, so the gamma distribution, basically, this is something like this, right? You can go, so here there is a shift. It doesn't start exactly at 0. At 0, this is something, so you have basically something and it decays exponentially. All right, so now let's go to the more interesting part in terms of the analysis. Let's discuss now the statistics of the shortest one. Question number 2. Statistics of the shortest telomere. The statistics of the length of the shortest telomere.
But with this already curve, could you integrate up to L0 and then determine what fraction of cells are expected to die at steady state, in a way?
Well, the reason that, you mean ignoring the fact that you're interested in the shortest one?
Yeah, because this already gives you...
Yeah, this gives basically the distribution of the length, but...
Is this for one?
This is for one, because let's assume that they are all independent. So basically it gives you the distribution for all of them. So let me show you what we did with this. So we were indeed interested, you have 32, and now this is, so you have 32 in here, so you distribute now 32 of these guys. You shuffle everything and say, all right, where is the minimum one? So this is really the statistics we're interested in. This is called extreme statistics. There is, in statistical physics, there is a branch that is going into that direction to look at extreme events. So basically this is, we can call this extreme statistics, but this is really looking really at the minimum of the distribution. So we have, let's say, x to x32. Let's call x1, x32 the length of them. So let's call it y. Usually this is called like this, x1. Let's assume we have, I call it 2n. We have 32, I'll call 2n of this. Now, what is the probability distribution for y? Now, this is not very hard because we just calculated the distribution function for any of them. So take the probability distribution, take 1 out of the 32. So we have this 2n. Let's take the distribution, so we call it f of p, f of x, that the probability that the shortest one is equal to x. And necessarily, the 2n minus 1 have to have a length which is larger. So what is larger? You have to, if you integrate this from 0 to any x, from 0 to x, this is the probability that it is less than x. So you want 1 minus this, so you have 1 minus f of x. And the probability, because they are independent, that they are with power, it's power 32 minus 1. So let's call it 2n minus 1. And f of x is 1 minus, so this probability is all that shorter, less than x, which is 0 of x, f of, let's call it f of y dy. Okay, so now we are in business. This is elementary analysis. How do you calculate the length of the shortest? We have the distribution for the shortest explicitly, because we spend a lot of time calculating the distribution for any of them. So what is the mean? What is the mean of the length? So we have to look at the first moment, right? So let's call it y, mean like this. So this is just y, d dy of the probability that, let's say, the mean length y is less than y. This is by definition, this is the moment. This is the first moment, the length, according to this distribution. So this is the distribution of what is written exactly here. This is exactly fy of x. But now you can, if we integrate by parts, this, you'll get exactly, so you integrate by parts, you differentiate this and you integrate this. And what you get, you have to integrate these guys. And this guy is going to be exactly sum from 1 to infinity of 1 minus capital F of y to the power 2n dy, which is f of y is here, the integral of f, which is what we calculated. So now this is interesting because let's assume n is large. Then how you estimate this integral? You just do Laplace methods. Laplace method in dimension 1, so this is very well known. And from this you can have an estimate, and the estimate is gamma 1 divided by alpha alpha gamma of alpha to the power 2n, 1 divided by alpha, where alpha is 1 plus 1 over b. Alright, you don't have to memorize this. But now we plug numbers and we find out that m is 184 plus minus 25 next test. So this is the mean, and we calculate it with y squared to get the standard deviation. We did Laplace methods when it is squared. There is an additional term here that you have to be careful. And this is what you can get. Now, next stage was to do the same for the mean first passage, for the length of the second shortest.